Hello, everyone. I knew it. I knew it. I knew it. I knew it. The first comments that I'll be reading would be this. Hello, Satish sir. Hello, Rajiv sir. Hello, Devcharan sir. It's the same room with different angle. Yes. And it's in front of me natural light. That's why. Room tour देने लायक नहीं है. Otherwise I would have given you the room tour. ठीक है. यहाँ पे as usual एक chair है जिस पे बहुत सारे कपड़े रखे हुए हैं. फिर यहाँ पे और कुछ सामान है जो यहाँ हुआ करता था. That has come here. Yes, this room is my workplace. Absolutely. Absolutely right. Okay. It's the same room, different angle. Everyone. I take class from this room only always. Sir, working on new YouTube video. No, not working. Yeah, guitar is on this wall. So usually you see this wall. Right now you're seeing this one. Okay. TV is here. Okay. सर आप नहीं वो मोटिवेशनल स्टोरी में YouTube VJE पे. हाँ, मेरे मोटिवेशनल सेशन बहुत प्राइवेट होते हैं ना इसलिए. I take my motivational session only for you guys. Okay. I'm good guys. Thank you for asking. Quickly say hello to your class teachers, Satish sir, Rajiv sir, and Devchandan sir. Quickly, everyone. everyone. Fatafat jaldi say hi to your class teachers. Yes, so that we can begin our class. This is our session number 2. Yes, this one is the session which got, you can say the one which we could not end up on Monday. We have replaced this one for today. Okay. Yes, absolutely, Aditya. You can ask me your doubts as usual at the end of the class. Everyone is ready? Can we start? Can we start, everyone? Yes. Cool. Awesome. Very good. So switching off the chat so that we all focus on the screen, right? So what were we studying last time? We actually did only the introductory part of fluids in the previous class, which was last night. Okay, so we defined majorly one very important quantity which we call as pressure, and we understood that pressure is basically applied by a fluid. Fluids are basically liquids or gases. In this chapter, though, our discussion will mostly revolve around liquids. So when do we say that a liquid will try to apply pressure? It's because someone else or some other body is trying to apply a force on the liquid, and liquid actually wants to travel to that body. That means maybe on Earth it is the body of the Earth which is trying to pull all the liquids towards itself. But if you fill the liquid in the container doesn't let the fluid comes down. So that is why fluid start exerting a force which is distributed over the entire area of cross section of that body. Okay. That reminds me that I forgot to bring my bottle. So just give me, okay, after this recap, I'll bring my bottle and then we'll take it from there. Anyway, so if we say that an external force is acting on the fluid and the fluid is being resisted by a body of maybe a container, that container is going to experience a force per unit area, which we define as pressure. Pressure is going to be a scalar quantity, a very important point to remember. Okay. Similarly, we define another quantity called as density, which is something which we already know and have a very good idea about that. That's mass per unit volume. So again, another scalar quantity has units of kg per meters cube. That's a unit. Okay. Then we define the pressure due to liquid column. When we say liquid column, whenever liquid is filled inside a container, only because of the liquid's mass. Okay, the pressure which it is going to exert is the mg of the liquid column. Liquid column, I'm again repeating because for that height to which you are interested in, to that height, if you divide that by the area of cross section on which it is applying the pressure, okay, that force per unit area, mg divided by area, we did the derivation, it eventually results in rho gh. And we understood that this is what we call as the gauge pressure. If you add atmospheric pressure on it, it will become absolute pressure. Okay, what is atmospheric pressure? Just like liquid filled in a container, we are actually surrounded by a lot of fluids. Fluids are basically the gases also, right? So those gases are also being attracted by the surface of the Earth or Earth itself. So they are also being, experiencing a lot of surfaces on which they are colliding continuously, and they are exerting the force per unit area, which we call as the atmospheric pressure. The value of atmospheric pressure is something that we will always keep in mind is 1.01 into 10 to the power 5 pascals or Newton per meter square. Okay, don't worry, we will be not today, but we will be speaking about something called as Pascal's law. And when that time comes, I will be explaining that. Somebody asked me that in the chat box a few minutes back. Okay, guys. Then we spoke about the force, which is or average force, which is exerted by a liquid on the vertical walls of a vessel. Okay, so that is something that we derived. We found that the average pressure is nothing but half of rho gh. So if you multiply this half of rho gh with the area of the wall on which you are interested in calculating the force, that will give me the value of the force itself. And that's what you see here in the expression of force. 1L into h is being multiplied. Length into height is basically the area of that wall, vertical wall, in which we are calculating the force. Okay. And how did we reach to this average pressure? We realized that only because of liquid at the top of it, the pressure is 0, and at the bottom of it, the pressure becomes say h rho g, if the height is h. So if I put the value of P1 and P2 here, I will be actually calculating this expression rho g h by 2. Okay, everyone, we understood this. We also spoke about two very important points which we'll be actually covering today also. One of the points I told you that to a given layer, on a given layer of the liquid, any given layer, liquid is obviously in the form of layers. At any given layer, the value of the pressure at different points will always remain the same. Secondly, the pressure which is exerted by the liquid column is independent of the shape of the container. Whatever be the shape, as long as the height to which the liquid column is filled is same in two containers, the pressure at that given point below that height h is always going to be the same value. Okay, there is one more interesting property that we'll be witnessing today. That's a very beautiful property. Okay, the applications are limited, but it's a very beautiful property. We'll come across that in some time. So one type of questions we did not do last time, so we'll be covering up that today. Okay, say you have so far we were discussing only one of the fluid only to be filled in a container. There was only one fluid inside the container. What if you have two or more than two fluids which are placed in such a way that they're not mixing with each other, like oil and water? You know that oil floats over the surface of the water. And in that arrangement, say you have a container which is closed. Okay, so this one is closed surface. And basically closed so that there is no atmospheric pressure which we are taking into account at the moment. And from A to B, the column height is h1. Okay, and from B to C, the column height is h2. Between A to B, the liquid which is filled has density rho1, and between B to C, the liquid which is filled has a density rho2. Okay, obviously the density of rho1 will be less than rho2. That's why it is floating over rho1 will be having lesser density. That is why it is floating over rho2. Okay, so rho1 is less than rho2. Oil has lesser density than water. That's why it floats over its surface. Fine, everyone. So we want to find out what will be the pressure at layer A or AM, layer BN or layer CO. Okay, so we know that the liquid will create pressure because of its weight above that height. Okay, so at point A, there is no liquid column over point A. So what do you say in the chat box? What do you say will be the pressure due to liquid at A or layer AM? Can we say 0 because there is no h only? So this is very easily we can find the value comes out to be 0. Now let's try to find out the pressure due to rho1 or height h1. Would you like to take a guess for point or layer A and BN? Will it be rho1 into h into g or rho1 h1 g? Can we say that rho1 h1 into g? It should be that, right? So let's see how it comes. The answer is the same, rho1 into h1 into g. So we know that it's going to be the weight of this portion divided by the area. Let's say the area is s, the area of cross section. Okay. Now if I want to write the mass, I'll have to write as density into volume. So density is rho1. Okay. Volume is area, that is s. Height is h1, and multiply that by g, divide that by s. S and s gets cancelled. What we expected, rho1 H1 into G. That's basically the pressure due to that column, and we already have derived this. The more interesting and more complicated part is layer CO. Okay, so guys, will the weight of liquid of density rho 1 or liquid 1, will the weight of this also create pressure on the lower liquid? Think of it like solid bodies. So if you are standing here, I told you that if you have something placed over you, can we say that if you have two blocks placed over you, both of them will create the stress on your head, right? Both of them will give you the stress. So that is why the pressure on the layer, bottommost layer, okay, the bottommost layer will have pressure due to rho 1 and pressure due to rho 2, both. Okay, but let's see how we get that. Okay, so everyone, definitely the pressure is going to be m1g plus m2g. Okay, derivation is not important, don't worry. So how will I write the m1 value? We already know this. It is rho 1 into s into h1 into g. We have already written that. But for this portion, if I want to write down the mass of liquid in region 2, the density is rho 2, the volume is s into h2 now. Only this much height will play the role in the mass of that into g and divided by the surface area s. So you can see that s is going to get cancelled. S cancels here, and what you are left with, you can take g common. The pressure at that point, which is at the bottom, CO layer, comes out to be rho 1 h1 plus rho 2 h2 into g as the answer to pressure P2. I hope you all understand this. Everybody gets it? I would have directly told you that it is rho 1 h1 g plus rho 2 h2 g, but now we have seen the derivation also. Okay. Yes, so remember, you just have to consider both the liquids, their pressure will create, or rather their mass will create the pressure at the bottommost point together. Okay, so let's see if you can solve a question based upon this. Okay, this is a question which has come in JEE Main 2020. So it's similar kind of situation, and the liquid is also covered. Okay, so liquid is covered. There is no atmospheric pressure playing its role. Question says that you have two liquids of density rho 1 and rho 2, while rho 2 is double the density. So that means if this is rho, okay, just a second. So if this has density rho, this has density 2 rho. That's what the question tries to say. Okay, it also says that each liquid, rho and 2 rho, has the height of 5 meters each. The liquid column value is also given to be same. Question says, what will be the ratio of the force, the average force obviously on the vertical wall, okay, on portion Mn, the wall which is vertical Mn, and the force which is applied on the wall which is NO. This is point O if you are not able to see that. I'm not able to see. So I don't know whether you are able to see this or not. Okay, O point is somewhere here at the bottom. So definitely the liquid will try to exert a force here, that is F1 and F2. Obviously that force will be dependent on the average pressure value. So P1 and P2, the average pressure you will have to find out on the wall Mn, and P2 and P3, the average pressure has to be found on NO, and then multiply that by the area also. Okay, you can consider the depth of the container to be L. You can consider the depth, means there is container going inside, right? So that you can write down the area. Cool, everyone. And what else? You have to find out the ratio of F1 to F2. What do you think will be the value here? I hope you remember how to calculate the average pressure. Giving you people 90 seconds for this. Okay, and your time starts in 3, 2, and 1. Should I switch on some light? Nah, doesn't make much of a difference. Okay. Last 5 seconds now. Okay. Still a decent number of people got this. I was not expecting that much. Okay, everyone. So let's solve this. Let's try to find out the value of P1. Can I say P1 will be equal to 0? Right? P2 will be equal to rho into G into H. So rho into G into 5, right? So 5 into rho into G, correct? And how about P2, P3? P3 will be equal to what? Can I say pressure due to upper column and pressure due to lower column, correct? So pressure due to upper column is 5 rho G. We are basically trying to write this. Rho 1 H1 plus rho 2 H2 into G. Okay, so H rho G because of upper column, and density is double. That's the point where I'm sure many of you made mistake. The density when you wrote for the second one. So this comes out to be how much? This is 10 plus 5. That means 15 rho G. So we have the pressure value at layer topmost layer, then layer N, and layer bottommost. Okay, everyone? Are we all getting this? Okay, so what will be the value of, so H2 should be 10 na? What was H2? Was it 10? Sudhir? What was H2? H1 plus H2 or just H2? Understood? So P1 plus P2 by 2, the average value is 0 plus 5 rho G by 2. Okay, and similarly P2 plus P3 by 2, that is 5 plus 15, 20 rho G by 2. Got it, everyone? Can I say that the area of wall Mn and area of wall On will be same? Do we agree? F1 by F2 will be equal to 5 rho G by 2 times the area. Why 2 times? Because this is denominator 2. Similarly, 20 rho G by 2 multiplied by the area. What do we get? Easy? 5 by 20 or 1 by 4. JEE Main question. This is a pretty good, decent level of question, I would say, for JEE Main. We have seen so many, much more simple questions comparative to this one. Okay, so we have the answer. Answer comes out to be option C. Okay, everyone. Okay, so now force is pressure divided by area. Aman Aditya. Last time only we did this. The average pressure is found as pressure divided by area. I did not divide by 2, I divided by A only. The pressure has the value of 2 in the denominator. Prithvi Teja. Yes, Arshan, we always calculate average pressure, average force only. And I wrote specifically the average force. Okay. Chalo, everyone, switching off the chat so that we focus on what we're going to study today. We'll be speaking about something which we call as the force, not just vertical force, I would say the force on the walls of the container. And when we are speaking about this is basically, now we'll be speaking about cases when the container does not have vertical wall. If the container has slanted wall, or say any plate inside the liquid is placed and it is not vertical, rather it is inclined to some angle. Okay. And something called as hydrostatic paradox, which we already have studied, we'll be revisiting it. Okay. So everyone, let's first speak about what happens if inside a liquid you do not place an object like this, you rather place it like this, making an angle. So now what will be the value of the force applied by the liquid pressure on this, right, everyone? So first of all, let's have a look at the diagram here. Okay, let me first simplify the diagram for all of you to understand what is happening here. So your actual plate, okay, this is your actual plate, and this is only the cross-sectional view. This is only the cross-sectional view. That means this is how you are able to see it. Okay, not even this. They are showing you in this way. That's why this portion that you see, is written over there as B. Okay, that's not a rod. It's not a rod. It's a plate. Okay, everyone, a plane or a plate. So this is B and this is A. Okay, everyone, tell me the value of area of the plate. If this is A, this is B. A into B is the area. Perfect. Okay, awesome, very nice. So be patient, try to focus. This is interesting and very simple to understand. So everybody, so plate has two layers which are at different heights or different depths. So maybe you talk about, say, position of layer 1 and position of layer 2. This is layer 2 and this is layer 1 of the plate. Okay, so what's so special about them? If this is the liquid layer, okay, or liquid free surface, then the end or the line or edge number 1 is at, you know, this inclined length represented as L given to us. Means they, what have they done? They have actually taken the length along the side A. Means what? They have taken this length. Instead of talking about the vertical length, they're talking about this length which is along the length of the plate itself. So this is given to us as L, and this angle is the one which is made by the plate with the horizontal or with the layer of the liquid. Okay, everyone. So can I say that the edge 1 will be at a depth which is L sin theta in the chat box? This is the depth of the edge number 1. This edge is at a depth. Depth matters to us, right? So it is at L sin theta. We can call it H1 also if we want. Okay, everyone. Cool. And if we speak about the layer 2 or surface or edge 2, you can see that this becomes L plus A. So the depth of edge 2 will become L plus A sin theta. Do we agree? Right, everyone? First of all, tell me, can we write the value of pressure if we know the depth and if we know the density of the liquid? Can we write the value of the pressure at edge A and edge B? So let me first just write that, just so that we understand what is happening in the derivation. Okay, so layer 1 or edge 1 will have a pressure which is going to be rho into L sin theta into G, or rho into G into L sin theta. I can write that, right, everybody? Similarly, pressure at edge 2 will be rho into G into L plus A sin theta. That's the difference. Okay, everyone? Cool. Now, can I say that if I have an imaginary vertical plate, that imaginary vertical plate is such that it is more like the projection of the actual plate. Means what? The vertical projection of this plate. Why we are talking about this projection, why we are talking about this imaginary plate, is because, say, if I say that this is the edge number 1 for the imaginary plate, and definitely the edge number 2 is shared with the other one, can I say that the value of the pressure at this edge 1 and edge 2 of the imaginary plate will also be the same? P1 and P2 will be same for the imaginary plate also. Do we agree? Absolutely, because pressure in the same layer is always same. That means pressure at point 1 and pressure at point 1 has to be same. We get this, all of you? This is one of the very key points to understand. Now, we always try to make our life easier in physics so that we can easily understand and we can solve questions and we can actually create parallels for our better understanding. Now, everybody, we know that the liquid always applies the force on the solid perpendicular to the surface of the solid. Do you remember this from the previous class? The liquid will always exert pressure, a force which is normal, which is perpendicular. So actually, the force is applied like this. This is how the liquid is going to create the force. Do you understand? Do you agree? Correct, everyone? So what we'll be doing, we will be actually talking about two components of this force. We'll be talking about two components of this force. One will be horizontal, one will be vertical. We will first find those two forces and then we will find out the resultant. That means we'll be then calculating the value of the F. Is the plan of action clear? Is the objective clear to all of you? We have already found the value of pressure. We know the area value already. And now we know that this force has two components. One is horizontal, one is vertical. We'll first find out those two components and we'll find the resultant. Both of them are perpendicular to each other for sure. Okay? Only one more thing before we get into more derivation. If this plate area has value AB, if the surface area of the actual plate is AB, can I say that this area of the imaginary plate will be AB sin theta because this angle is theta? In this imaginary triangle that you see here, this plate, imaginary plate, will have an area that is AB sin theta. Okay, everyone? Cool? Very nice. Okay, perfect, good. So now we will, let me make it much more easier for everyone to understand from here, and then we'll see the actual derivation written already. Okay, so I'm just drawing the cross-sectional view of the plate. This is the cross-sectional view. Okay, and this is its projection. This is horizontal projection, and this is the, sorry, that one the vertical projection, and this is the horizontal projection. What we have been given? We have been given that this angle is theta. This area is A into B. This is only the side view. Now you're only able to see the edge. You're only able to see this. From here, you will feel that it is only a rod, right, everyone? But it is actually this. So you're only able to see this part. So we are saying that this thing has area A1. Okay, area is A1, whose value is AB sin theta. So definitely this one has area A2, which will be AB cos theta. And we have understood that the force which will be applied will have two components. Okay, so we are going to find out the value of those components of the force. So everyone, if we know the value of pressure P1 and pressure P2 on the two layers, here also the pressure is P1 because they belong to the same layer. We found the value of pressure P1. It came out to be rather rho into G into L sin theta. Okay, from here we got the value of pressure rho into G into L sin theta, and the other one, the pressure was rho into G into L plus A sin theta. Do we know how to calculate the average pressure? on this wall, the average pressure on the main actual plate, the average pressure is simply P1 plus P2 by 2. That means rho GL sine theta plus rho GL plus A sine theta divided by 2. Okay, half of this value. So everyone, see what is going to happen. This is rho GL sine theta. One more rho GL sine theta will come from here. So we can write it as rho GL sine theta plus rho GL sine theta will become rho into G into 2L sine theta. Okay, and from here one more term, rho GA sine theta. You can see that we can take rho G into sine theta common. So P average, everybody, comes out to be half into rho into G into sine theta, or we can say 2L plus A sine theta. Have a good look at what I have written. It's pure mathematics that we have done. Okay, everybody. Everyone understands this? Fine. All I have to do now is multiply the average pressure with the plate area in order to get the value of the force. Okay, everyone. So can I say that the horizontal force is equivalent of the force which is experienced by this wall? Can I say that? Everyone, can I say that whatever is the horizontal force is equivalent of being applied on the area A1? And the vertical force is basically the one which is experienced by the wall area A2. We agree on this? That will give me the two components very easily. So let's do that now. Okay, so I'm taking this diagram on the next slide so that we are able to do that. Okay. Okay, Shweta, no problem. You may not understand the currently ongoing slide, but this is not going to be related to the upcoming discussion, so no problem. Okay, so everyone, we have got the value of the average pressure. I'll take that also on the next slide so that I can easily write down the value of the Fx and Fy. Okay, so we have this also. Now, making the attempt to write Fx. Can I say Fx will be equal to P average multiplied by A1? Tell me if you understand this. Okay, so P average multiplied by A1 is like writing half into rho into G into 2L plus A into sine theta into AB sine theta. Everyone is okay? Everyone understands this? Correct? So what do I see? I see half rho G into AB into 2L plus A, definitely lengthy expression. That's why I do not recommend also to remember. Difficult to remember, that's why. So we have the expression of the Fx component. Have a good look. No need to remember. Just see that all the steps you are able to understand. Half rho G into AB into 2L plus A into sine theta becomes sine square theta. Okay, everybody? Nice? Good. Now I'll write down Fy. Fy is going to be P average multiplied by A2. And that's going to be half into rho G into 2L plus A into sine theta, which was already there in the pressure. And area A2 is AB cos theta. Okay, everyone. So here what do I get? I get the value as of Fy half into rho G AB 2L plus A multiplied by sine theta into cos theta. Do we all understand this so far? Looks lengthy but understandable. Okay, so we have the value of Fx and Fy. Cool. Let me cross check with the already written derivation. Half rho G AB sine square theta 2L plus A. This is what we get. Let's compare and tell me is it matching with equation number 1. It's matching, right? Half rho G AB 2L plus A sine square theta. So far we are on the right track. And let's also compare Fy. Let's compare Fy. Is it matching? Half rho G AB sine theta cos theta 2L plus A. So we are on the right track so far. That's good. Okay. Now we have Fx, we have Fy. How do I find out the resultant? By using the parallelogram law of vector addition, under root of Fx square plus Fy square. Okay. Right, everyone? So see this, under root of Fx square plus Fy square. The first force is written, the second force is written. Okay. What is important for us to see is when we are taking the two forces. Okay. This is Fh, this is Fy, Fv. Which part is common in both of them? Half rho G AB and sine theta. Do we agree on this? Half rho G AB and only one of the sine theta is common. From here, 2L plus A is also common. So from here, one sine theta will be left, and from here, one cos theta will be left. Do you understand? Rest things are common in both the expressions. So you see now the next slide will make sense to you all. You see that half rho G AB 2L plus A into one of the sine thetas are taken out. Okay, or rather I should say, we have taken sine theta and cos theta separate. So when you square that, everything is squared, and that is what is written here. Do you understand this step, everybody, or do you want me to write it on a lengthy slide separately? Understand, right? And what is sine square theta plus cos square theta? Things which we wish always come. Yes, the value is 1 here, and this under root value comes out. We have half rho G AB sine theta 2L plus A as the force which is acting on the walls of the container or the plate. Okay. You know what I want you people to look at this here. If L becomes 0, what is L? Let's have a look at it one more time. If L becomes 0, that means what? If the liquid layer is just at the edge 1, means this is what is the layer also. Getting? Then what is the expression that we will get? Then we'll get the value of F as half into rho into G into A square B sine theta. Getting? Everyone? This is the expression that we get. I want your focus only on this part first. Except sine theta, just have a look at it. Just have a look at it, guys. Except this sine theta. Half rho G A square B. Half rho G A square B. Half rho G A square B. Do you see similarity with the average formula we found last time? Right, everyone? So what we are doing actually on this, we used to earlier have the force horizontal. Now the force has gone to an angle. Okay, the force has gone to an angle. That is why this is happening. We have this as Fx, this as Fy, or let's call the forces to be Fv and Fh. This is actually the force. And the angle, let me understand the angle once. They have made this angle as, okay, so this angle is given to us as theta. Okay, so if this was the force earlier, which we used to find out. Okay, let me just reconfirm with the angle once, everyone. If I have this, the force acting, that angle is theta, so this becomes 90 minus theta, this becomes theta, correct? So angle theta has been drawn right here, everyone. So are you guys getting that if this angle is theta, what we used to calculate as the force which was acting earlier was only the sine component, or rather the force which we used to calculate earlier, now this force is only the sine component of that force. Okay? So do I need to remember? If I need to remember, I'll rather remember this part, that I have to just multiply it with this angle theta. Okay, cool. So if ever we get into a question where walls are not vertical but at some angle, just remember that that angle is this one, made with the horizontal layer. It's not made with the vertical. This is not the angle. Okay, this angle is 90 minus theta. So remember which angle was defined as theta. Okay, yes, you don't need to remember the derivation, not at all. Yeah. Sure, derivation is not important anywhere. Okay, Priyanshu. So okay, now the paradox. First of all, what do we mean by paradox? Paradox is basically things which are coexisting but they seem contradicting. Things which are coexisting but they are contradicting. Those things are called as paradox. Okay. So what is hydrostatic paradox is something that we already know. Something that I told you guys already. That if you have liquid column filled to the same height in different liquids, then the pressure at the same depth in the liquids is going to be same independent of the shape of the container. So what we are saying here, that the depth is h, density is rho, acceleration due to gravity is g. So at the bottom, okay, at bottom, just an example of bottom, any layer you consider which is at the same depth, you have to just fill the liquid to the same height. That's the only criteria. Okay, everyone, please remember the criteria is very important. It's not about filling them with the same mass of the liquid, rather you have to fill it to the same height. That's very important. So the pressure at A is equal to pressure at B and equal to pressure at C, and you can look at the container and see that weight of liquid in one will be lesser than what is there in B and will be even lesser than in C. Means mass of the liquid is more in C, lesser in B, and further less in C. But the pressure value will be same at the bottom of all the three containers because they have the same height to which the liquid has been filled. So this is basically the paradox. Weight is different, but pressure is same. They are coexisting. They are a little weird. That's what we are saying. Okay, everyone, can you keep this in mind? Can you remember? It's a very important point to remember. Very important because many questions will be and have already been done on this point. Okay, independent of the weight, and definitely have to fill the same liquid. You have to fill the same liquid obviously in the different containers. So another demonstration shown here. The height of the liquid in the vessels are same, but they have different shape. So different amount of liquid is there, but they are still having the same amount of pressure. Okay. Base area need not be same. Base area same hai hi nahi, in fact, you can see this. Base area need not be same. They have kept it same so that it looks like it's a weird part. Means what? If you will try to find out the value of pressure, you might think that okay, different areas, so maybe that is playing the role. Even when you keep the pressure area also same, they will still have the same pressure. If you change the area also but keep the same column, means what I'm trying to tell you, say I have this bottle which looks like this, and whatever is the area, I fill liquid to a height say 15 centimeter. Now I take a bigger container, but I fill the height only to a 15 centimeter only. The pressure at the bottom of that bigger container and the pressure at the bottom of this bottle will still be the same. That's what we are saying. I'll give you a practical, example to relate to it. I'll give you a practical example. W is weight. मतलब अब तो यार ये चीजें तुम guess कर पाते होंगे, मैं expect करता हूँ. So everyone, just listen to me now. Okay. Arey Harshan, they don't have the same weight. That's why the height is same, but the mass is not same. Okay. At any layer, if you consider the pressure at a height h/2 also, those 3 points will also have the same pressure, same level. Yeah. Now listen to me on this, everyone. Those who know how to swim will be able to relate to it better because they have been in water. Okay. Say you go to swim in a swimming pool, and initially when you dive, you are going further deeper, and say you are able to go down by say 5 meters. Okay, this is the realistic one. So if you go down by 5 meters, there is certain pressure that you will feel on your ear. Okay. If you ever in your life, or if you have already done it, if you ever take a dive in a river or in say, I don't know, ocean, you will feel the same pressure at the same depth. You'll feel the same pressure at the same depth. And you know that comparative to your pool, the river is bigger, ocean is huge. But because you are going to the same depth, the pressure value will be same. Okay, everyone? So those who know how to swim, if you ever get to try this, test this, and if you remember that there is something called as hydrostatic paradox, do try that. Okay? So, okay, everyone. So, chalo, we are moving very slow. Let's move forward. Let me show you an example here. Okay? This question has this diagram which says that, in this container, which is more like a tube, you have liquid which is filled here. So it says that if you look at this layer, the red line that you see, you can see that the left end, or end number 1, has additional liquid column over here. Okay? By whatever means that has been done. And here you have some different situation. The pressure is P, small p, and this pressure is capital P. Notice the difference. Small p and capital P pressure. So the difference is actually the height of this liquid column on the left side. Okay? The density of the liquid, it is water, so it is rho into V. Question is asking us to comment about the value of the pressure at point P, or rather at the question is asking us to compare the pressure capital P and small p. First of all, let me ask you people only. If I speak about point A and point B, will they have the same pressure? P A and P B, will that be same? Because they belong to the same layer. Technically, they belong to the same layer. Okay. So can I say that if I go little up from A to go to this point C, what will you say? PC is greater than PA, or is it less than PA? Quickly. Should be lesser, because more you go in the depth of the liquid, the pressure increases. And we know that pressure at A is equal to pressure at B. So from here only, we can see and say that pressure at C will be less than pressure at B. And this results in capital P being less than small p. This is the analytical understanding of it. Do we understand this? That capital P is small than smaller p. It is less than smaller p. That means the correct answer is option B. Okay, yeah. But have a look at this also. We know that pressure at point A and that pressure at point B is same. PA equal to PB equal to P. So at this point A, if I want to write down the pressure, it is capital P pressure plus the pressure due to liquid column, which we call as gauge pressure. So capital P plus rho GH is the pressure at A. But we know that pressure at A is equal to pressure at B, which is given to us as small p. So I equate that to P also. So capital P plus rho GH is equal to small p. So I take this on the right hand side and I get the expression as small p minus rho GH. That means from small p, I have to subtract this value, then only it becomes equal to capital P. So this proves mathematically, or we can say analytically, that the value of capital P will be less than small p. Okay. We already got the answer from here already, just by using the basic logic of pressure, and we got the answer. Okay. Cool. Chalo, a few quiz questions for all of you guys. You have to select the wrong statement about pressure. Options are written here that pressure is a scalar quantity. Pressure is always compressive in nature. That means whichever solid comes in contact with it, it tries to compress it. It tries to decrease the volume of it. Pressure at any point in the liquid is same in all the possible direction, or none of these is a wrong statement. What do you think? Giving you 30 seconds, and the time starts in 3, 2, and 1. Okay. I'm expecting many people to answer as option C. I don't know why. Oh, most of them answered it as option B. Guys, all the three statements are right. We already know this. Pressure is a scalar quantity. We actually talked about it that liquid tries to apply force normally to the surface of a solid. Okay, so maybe if liquid is filled here, and say you place a water bottle or any plastic bottle inside, the liquid will try to compress it from outside. And in fact, if you people remember, we spoke about the situation that if we empty a plastic bottle, it will be crushed by the atmospheric pressure, because atmospheric pressure is also being created by fluid, which is the atmospheric gases. So pressure is always going to be compressive in nature. It will try to compress the body. Okay. Third one, because pressure is a scalar quantity, at a given point in the liquid, the pressure will try to exert the force on all possible points which are nearby. So the value of the pressure at any given point is same in all possible directions at that point. Means what? I can calculate the pressure, force due to pressure at this point. Okay, maybe this point or this one or this one or this one. Very close points which are on the same layer they are. So the value of the pressure will be same in all possible directions. Okay, so remember these are all correct statements. Another one for all of you. We have been given two containers, P and Q, and they have the same base area, capital A, and they each are filled up to same height with same liquid. So what do you think? You will comment about the pressure at point X and pressure at point Y in the two containers. Options are there in front of you. Giving you again 30 seconds, and the time starts in 3, 2, and 1. Okay, and the time is up. Good, very nice, very nice. This was expected to be correct for all of you. Doesn't depend upon the shape of the container. The value of the pressure at the same depth, you can see visibly only that they have the liquid filled to the same height, and it was mentioned also in the question. So that's why the pressure at X and Y point will be same, as they are the same liquid points and they are also at the same depth. Okay, sure, everybody. Let's move to the next topic for today, and that is accelerated container. Means what? Maybe the liquid is filled in the container and it is stationary with respect to the container, but the container is accelerated. So if the container is accelerated vertically, what happens? If it is accelerated horizontally, what happens to the liquid? We'll first speak about the situation when the liquid is accelerated in the vertical direction. Okay. So before I show you the slides, let me just give you a very easy understanding of this. So maybe you have certain liquid which is filled in a container. And only speaking about the gauge pressure, the pressure which is created by the liquid column. So maybe to a height h you have filled it. Okay. And when the container was not moving, then we know that the value of the pressure at a depth h, you can calculate at any h. So I've taken it as the entire column, and I'm talking about say point x, which is at the bottommost layer. So we write the pressure at x as h into rho into g. No problem with that, right? Everyone? Everybody's convinced with that already. Now what I'll do, everyone, I'm going to accelerate this container. Okay. Container accelerated upwards with an acceleration a. This is the first acceleration case, right, everybody? So if you are one of the observers which are also present inside, if the container starts to go up, will we experience any pseudo force? Even with the absence of the liquid, we do, right? So liquid also has mass, and liquid also has mass. So can I say it will also experience the pseudo force, right, everybody? So what was happening in the previous case? The only force which was acting downward was gravity. So only acceleration was acceleration downward, even when the liquid and the container was stationary. Okay, container at rest. This was the case. Now, people, when the container is accelerated upward, and I'm looking at it from the non-inertial frame of reference, that's why I'm not showing you the acceleration direction. Can you tell me the direction of pseudo force, upward or downward? It is downward, right? So what will you say is the effective value of G? G effective. G plus A or G minus A? Can I say it will be G plus A, because pseudo force will also act downward. So this is pseudo force acceleration due to pseudo force. Please don't get confused that, sir, in the statement you have written acceleration is upward, but you are showing the acceleration downward here. Hope you guys will not get confused with this. Okay, solving it from non-inertial frame. Okay, everyone? Yes. So what will I say now? The new pressure value will be Px dash will be h into rho into g effective. Okay, that means h into rho into g plus a. That means now at point x, the pressure reading will increase, because we know that if there would be a weighing machine placed at the bottom, of the container, the reading of the weight will increase. So if the reading of the weight is increasing, that means more force is acting. If more force is acting, pressure will also increase. We get it, everyone? Perfect. Cool, nice. And the third possibility is container accelerating downward with A. Now what will happen? Again, we'll speak from non-inertial frame. Okay. So let me bring the observer. That's why I'm drawing the person here, so that we understand it's a non-inertial frame of reference. So we'll say that G is acting downward, but acceleration due to, or rather pseudo force acceleration is upward. So G effective will be equal to G minus A. Okay, everyone? So what is going to be P x dash now? It's going to be h into rho into G effective, and that is going to be h into rho into G minus A. I hope you all understand this. This was h rho G plus A, and this one is h rho G minus A because of the pseudo force. Okay, yes. So I've already explained you what happens when the container accelerates upward or downward. Okay, so that's what is written here also. Say if you have a container, when the container is accelerated, they have only spoken about one of the cases. We have spoken about both the cases. If the liquid is accelerated upward, only in this column whose height is z, the final expression we already know is h rho g plus a. So z rho g plus a, z rho g plus a should be the answer, right? So z rho g plus a, that's the answer here. So how they have done it? Let's have a look at that also. So what happens, guys? Because of the liquid pressure, if you consider an imaginary cylinder, or you can say the liquid cylinder, imaginary liquid cylinder, then pressure will always try to compress the cylinder, right? So if you look at this topmost surface of the imaginary cylinder, this will be the force, say Fa, or rather this will be Fb acting to compress it downward. Similarly, from the bottom surface, the force will be Fa acting so that it can compress. So the force's direction has to be like this. It will always be normal. It will always try to compress the body itself. But on the curved surface, all the layers are going to have the pressure on that given layer to be same. So at a given layer, all the forces that I will consider, they all will come out to be same. Okay, so horizontal forces will always cancel out each other. So that's why there's no horizontal force taken into account. So say the area of cross section of this is delta S. So the force, okay, this what you see here is force at A, which is going to be pressure at A multiplied by the area. It is acting upward. Similarly, force at B is pressure at B multiplied by the area, and this one is acting downward. Which point will have more liquid pressure, A or B? Let me see how much you guys are understanding this chapter. The one which is at more depth, right? Which one is deeper, right? So A is the one which is at deep level. So the pressure at A is greater than pressure at B. So definitely the force at A will be greater than force at B. So everybody, what is the effective direction of the force on this imaginary container? What is the effective direction of the force acting on this container? Are you all sure? Effective direction has to be upward. Okay. Fa is stronger than Fb. I am telling you that is true. Okay. So that means what? Even if there is a solid body inside a liquid, what is that force which it is experiencing because of liquid pressure? It is always upward. Because of liquid pressure, a body inside the liquid will experience a force that is always upward. Do you know what this force is called? Do you know what this force is called? Yes. Though today we are not discussing buoyancy, but I've already given you the idea of buoyancy. Why the liquid throws us upward. When we take a dive in water, the water always throws us upward because of this. Okay. This is the mathematical explanation of buoyancy or buoyant force. The direction of the force will always be upward when a body goes down in the liquid. Okay. Cool. Everyone, switching off the chat so that we focus once again. So if we find out the imaginary weight of the cylinder, it's going to be area of cross section into height into density into g. So mg we have written here, and that is acting downward. So everyone, we can say that mg is acting downward, fb is acting downward, fa is acting upward. So we can say that fa will be equal to fb plus mg, right? So that is what is written here. Now if the container was stationary, the situation was this. This was equated to 0. Now what they are saying, the container is going up. So can I say that this imaginary cylinder is also going up with the container? And when a body has to move up and accelerate, the upward force should be stronger than the downward force. So my bad. This is what will happen because the container is accelerating upward. Do we all understand this equation? Everyone? This is upward force equal to mass into acceleration. Okay? So take mg on the right hand side becomes mg plus a. Write mass value as delta s rho into z. Delta s gets cancelled, and you land to that equation which we found very easily, by the way. We already found this equation. So we don't need to remember this derivation because I've given you a very easy understanding of what happens when the liquid is going to be in the container and container accelerates. Okay? Everyone understands? So this one is an alternate approach. If the container will accelerate downward, then the value of Fb plus mg will be greater than Fa. Fa will be greater than Fb only, but because of weight, okay, because of the weight, the value of this force will be Fb minus mg. Fb plus mg minus Fa will be equal to ma. Okay? No, Harsh, I'm not re-explaining it. You can watch the replay once again. Okay, Harsh, I have given a lengthy explanation there. After the class, just watch the replay one more time. Okay? We have a lot of slides to cover yet. Yeah, thank you. Now comes the most interesting part. What if I take the container and accelerate it horizontally? Will the liquid layer still remain horizontal? My first question. If the container is horizontally accelerated, the topmost layer, will it still remain horizontal? It will slant, right? It will slant. So there comes a very important point here, everybody. Always remember the free surface of the liquid. Do we understand what is free surface? The topmost layer of the liquid. Okay? The topmost layer of the liquid, it always remains perpendicular to the direction of effective acceleration. So you see that effective acceleration was either downward or maybe upward. It is vertical, right? The effective acceleration so far was along y direction, right, everybody? And that's why the layer remained horizontal when the container was accelerated upward or downward. Okay, everybody, you get it? Right? But now what will happen? The value of the effective acceleration, which was right now so far vertical, that will not remain the same. What will happen now? Let me just give you an introduction to that first. Say you have a container which is filled with liquid, which had this type of layers being formed. Okay, but now what happens? The same container is being accelerated horizontally. Okay, so if it is accelerated horizontally with an acceleration a, let me consider any point here. Definitely the gravity still continues to act downward. This is g. What will be the direction of the pseudo acceleration? Right or left? The direction of the pseudo acceleration will definitely be opposite to the direction of actual acceleration. So this becomes the direction of pseudo acceleration. And now do you see that the direction of effective value of acceleration is neither vertical nor horizontal? Can I say this is going to be the g effective direction? All of you? G effective is going to be a square plus g square. Okay. So the layer of the liquid will always arrange itself perpendicular to the direction of g effective. The layers of the liquid will always going to arrange themselves in a direction that is going to be perpendicular to g effective. That's the key to understand. Okay, I will write that also for all of you. The liquid layers will always be perpendicular to the direction of effective g. Okay. Difficult to write in your home because you cannot continuously accelerate the container. Okay, everyone. So I'll first show you the method which is there in the method which they will be giving you, then I'll give you a shortcut of that also. What is the shortcut and why do we need the shortcut? We need to find out at what angle with the container. Very strong word, sound coming. So we want to basically find out the value of this theta. At what angle with the horizontal the liquid layer gets arranged. So we basically want to find out this theta. First, I will show you the, you can say maybe the textbook approach, then I'll give you a shortcut. Yeah. Okay, everyone. So how they do it? Again, they consider an imaginary cylinder here. Okay. So this was the initial shape of the liquid, and now this is the final shape that you see. Obviously, the two layers, or rather the same layer, PQ. Okay. The layers are now getting arranged in this manner, as you know. Okay. So what happens? These layers that we see, they are going to become slanted. So here, what is happening? Say if I consider the free surface of the liquid, the point P and point Q were earlier at the same level and same height also. But now you see that point P has a different height h1 and point Q has a different height h2 with respect to a reference line, any reference line inside the container. Okay, the horizontal reference line that you see here, which we are taking as the side of, or you can say the length of the cylinder, imaginary cylinder of length L. Okay. So everybody try to understand this approach also. It might be helpful someday. So what we see here, this is the cross-sectional view. This is the imaginary cylinder, okay, of area of cross-section delta S, and it is at a depth h1. Okay, so this has become the new layer. Okay, the layer of free surface. Okay, this is the new one, or the new arrangement, and this one was the free surface old version originally when it was not accelerated. So everybody, do you see that pressure at PA and pressure at PB, the value of HROG will not be same now? It will not be same. Do we see this? Correct. So now we can say that at this point, the force which will be applied by the liquid pressure will try to compress the cylinder with a force that is Fa to the right hand side, and here the force which will be applied by the liquid pressure on the imaginary cylinder will be on the left hand side. Do you understand? It tries to compress the cylinder. Okay, everyone. But the cylinder is inside the liquid. The imaginary cylinder is also inside the liquid. It's the imaginary liquid cylinder only, and the container is accelerated horizontally. This is basically inertial frame of reference approach. Just this one also was the inertial frame of reference approach, right? Because we equated our final expression to ma. We equated to ma. So this one is also inertial frame approach. So what can I say? Can I say that Fa minus Fb should be equal to mass into acceleration? Do you agree? For just simple laws of motion approach. Perfect. Thank you. So pay attention, everyone. The value of force Fa is Pa into area delta S. Pressure force at B is Pb into delta S. So this is Fa and this is Fb. Okay. Direction also given, left and right. Fine, everyone. So we say that this is Fa minus Fb equal to mass into acceleration. So for the cylinder, if I have to write the mass, that is going to be density into volume. Density into volume is going to be the length of the container into the area of cross section. That becomes the volume. That's what is written here. Density into area into length into the acceleration. So what we did, we took delta S common, and now you can see that delta S gets cancelled. And what I'm left with here is Pa minus Pb equal to rho into L into A naught. Rho into L into A naught. Okay. And what is Pa? It is h1 rho g, because this height is h1. Okay. And what is Pb? Once again in the diagram, the height h1 will create the pressure h1 rho g. Height h2 will create the pressure as h2 rho g. We will write that h1 rho g minus h2 rho g equal to rho into L into A. Rho will definitely get cancelled here. So you'll be left with h1 minus h2 into g equal to L into A naught. You bring L downward and you take g also on the downward to the right hand side. So this is the final expression that we have, h1 minus h2 upon L into A naught by g. And everybody, look at this imaginary triangle here. Okay, have a look at this face. If this height is h1 and this height is h2, can we not say that this is basically h2 minus, oh sorry, h1 minus h2? We can say that, right? And that's the triangle they have drawn here, h1 minus h2 into L. So what is h1 minus h2 divided, sorry, not into but divided by L. h1 minus h2 divided by L is the ratio which we take for tan theta. So that's why we can say this value effectively is equal to tan theta. Tan theta comes out to be the ratio that is A naught by G. Okay, everyone? Do we understand this so far? Cool. Now the shortcut. Time for shortcut. Okay, time for shortcut. Everyone, remember this diagram, everybody? Remember this diagram? The only key to remember my shortcut approach is this. The only key to remember my shortcut approach is this. That the liquid layer will always be perpendicular to G effective. Okay, can you remember this, everyone? Right? Now see, this is the angle that we are looking for, the angle which is made by the layer, and liquid is, or other container is continuously accelerated, constant acceleration is what we are assuming. So people, if this angle is theta, will you not say this is also theta? Right? Can I say this angle is also theta? We have been doing this in laws of motion so many times. So everybody, time for a very, very, very simple approach. We need this angle theta. We have this as G. We have this as A, right? This right angle triangle I have drawn. Can you write down the value of tan theta from this triangle and tell me? Is it not A by G? That's it. Done. Done. Tan theta. It's not simple. Absolutely, it's not simple. Okay. But this is obviously from non-inertial frame because I've taken pseudo acceleration. My observer is present here to, he's risking his life by being inside this liquid. Don't know with oxygen mask or not. But this is what it is. Okay. 20 minutes derivation in 2 minutes. Yes, absolutely. So everyone, let me show you a very interesting question based on the same. Okay, so they're asking us to find out the value of the pressure at point A. I hope you all are able to see point A first of all. This is point A, which is at a height or rather at a depth h from the top layer or from the slanted layer, and it is at a length L from the rightmost portion. Okay, it is at a distance L from the right side. Okay. So if I draw the free surface, okay, and by the way, it has multiple correct answers. We can say that G value will be acting downward, or rather, I'll talk about g effective first. Can I say this is going to be the direction of g effective? Yes, that's going to be the direction of g effective. Also, we know that the actual g is acting vertically downward and the pseudo acceleration is acting left side. Okay, and because they have not spoken about any angle, so let me consider this angle to be theta. So far, so good. Can I say that g effective is going to be under root of g square plus a square? Yes, everyone understands and agrees also. We have been doing this so far. Okay, so now people, now the interesting and important part. We'll take it on the next slide also. So we have taken this angle as theta. Okay, guys, and now I'm going to join this here. And before I do that, let me just take this edge here. This is edge. Okay, be with me. Do you all see that h dash is basically the perpendicular distance from the layer, from the green layer, from the free surface? H dash is the perpendicular distance. Okay, it's a very important diagram for us right now. Okay, guys, now pay attention. We need certain more things. We know that this angle is going to be 90 minus theta. So can I say that this angle is going to be theta? Everyone, can I say this angle can be written as theta because this one is 90 minus theta? Good enough. This angle is 90 degree. This angle is also 90 degree. This is A. Let's call it B. Let's call it C, and let's call it D. So the right